So let's have a look at this exercise here, running jellyfish. First it says copy the code above, and that's the one up here, right? Save it in the module 3 folder and maneuver into this folder and sbatch to slurm. So this should be sort of a ready to run code. Let's see. I just copy. Then I go into RStudio, and now I have, of course, made myself a module 3 folder. So that I click into. Whoops, there was some old rubbish there. Let's see if that. Yeah, so now it's empty. Let's see if we can make a script here. New file and then a shell script. Not an R script this time. Shell, and then we just paste the code in here. And now we have to remember to save it. And then you also have to remember to save it in that folder, right? In the module 3 folder. So in case you have some choices here, you always have, make sure it lands in that folder. Jellyfish, I call it. And it should have the extension .sh, as all shell scripts should have. And here it appears. So now it's saved, right? And if I go back to if I go to my terminal, I have the module 3 folder. I step into it. I list the content, and here is it. Here's the jellyfish script. It's not executable, but it doesn't really have to be in order to run it in the Slurm. So now we were told to just sbatch, right? If we go back to the exercise. Now we have copied, maneuver into this folder and sbatch to Slurm. And that we do from here. Sbatch and then the name of the script. Like that. And if I now look at the queue with my username, I will see that it's now running. The job ID, yes, the same as we got up here. The name of the script, or the name that is used, and this is the name we put here, right? Under job name in the heading. And then my username here, and it's running, right? And the status running. And it's been running for 8 seconds when this command was executed. Now it's been running longer. It's on computing node 18. So if you have a short look at the script, we load the jellyfish software. Then we set some shell variables that we use locally here. For instance, this threads. And notice the value here, 10, must always match the number you put up here when you reserve the number of threads. Because this is where you actually reserve them. Here you sort of specify how many you reserve, and if we scroll down, here we actually use them. We could have typed 10 directly in here, of course, instead of storing it as a local variable and then use the variable here. But I find it's usually a good idea to, these are things we may change, right? The number of threads. And everything that we sort of want to possibly change later, we put up here, because then we can only change it up here. And we don't have to go down into the command line and change anything. I'm not 100% consistent in this, so you will see I divert from this, but I try to stick to that sort of general idea. Everything that we want to possibly change later, we store it up here as a variable of some kind. Yeah, and then some names of some out file here. This should be the final out file, right? This part here of the code is very special, I would say. This has to do with the fact that this jellyfish software doesn't really read compressed files, which is quite unusual. Most softwares will do that, because you notice the input files, the sequence data files, they are compressed. You can see it from this ending here. So if they were not compressed, we wouldn't need this at all. Actually, we could just use this directly as input. But since they are compressed, we have to sort of copy them, decompress them, and blah blah blah. That's all this. It's explained in the module document. And then we run jellyfish first to count the k-mers. And notice k is now 21, so it's pretty long k-mers. First we count them, and then we run jellyfish again to make this histogram. And that's actually the result we look for. If I go over here now and refresh, we will see that a log file has appeared, and actually this result file has also appeared. And if we go back to the terminal and look at the queue again, we can see it's ended this. So hopefully this ended successfully. You can actually click open the log file, but I can see already it's empty, which is usually a good sign. So some software will output some text to this log file, some don't. But if it's empty, it's a good sign, because if there were some errors, they will also be found in this log file. Okay, so possibly this one is now, let me click it open. It's not super big. It's a good idea to look if the file is big, because if you try to open very big files in RStudio, it will sort of hang, or it will take half an hour to open it, right? So please don't click on big files, because then you will sort of block your RStudio for a long, long time. But this is not a big file, and we can see it's actually a table with 2 columns. And these are the counts. So it's actually, when you count the k-mers, right, we count for each k-mer, get a count, how many times we see that k-mer. And here we count the counts again. So this many k-mers were seen once. This many k-mers were seen twice, and so on, right? Okay, so that was actually the first part of the exercise. So the next part says that we should make an R script now to read in these results and plot them. So let me just copy this here, which is sort of with a given that we should edit. And now I want to make an R script, right? And then I paste in here. So, and first thing I do now is to save this as well in the same folder, right? It's usually a good idea. And what should I call this? Jelly plot or something like that. You can call it whatever you like. And this should be .r. This is an R script. Before I do anything else now, I would like to make sure that I run my code in this folder here, because it's not absolutely necessary, this, but it's very helpful, I think, in many cases. Because I'm looking into this module 3 folder here, but this is not actually my working folder, because if you look at your console window, the path on top of that lists your working folder, and you can see this is still my home folder. I'm not sort of working inside the module 3 folder here now, and that I would like to do. And you can do it in 2 ways here now. Since we have a file open that lives in this folder, we can go to Session, set working directory to source file location. Then it will set the working folder to the same folder as this file is stored in. So this is one option. Let me show you another option. Since you also have the same folder in display here in the files, you can go into here as well and say set as working directory. Then this folder will be used as your working directory. And notice what happens up here now, up here at the when I click here, zap. Now you can see that now we are running inside the module 3 folder. And this is of some importance, because when we now want to execute the first line of code here, we read the file. And what should be inside here? The file name, of course. Count.txt. this file here, right? The result file. And notice I don't need any path in front of it now, simply because this file is inside the same folder as I'm running the code. This folder here. If I had continued to run R in the home folder, then I would have to type module3 / like this, right? To tell R to go down to the module3 folder and then look for the file count.txt. So you always have to make the path to the files corresponding to where you are running R. Of course, you can always use the full path, right? Like this. Then I would be safe, because this will work from anywhere in the system. I can run R in any folder and this will still work. So that is in some sense the safest solution, but it's a long typing. So I prefer the short version here now and hope that this will work. Let's see. Let's run one line. First, we need to load the library, the tidyverse. And then I run this particular line. And it looks like it worked, because here I got something. It looks like a table, 947, but it's only one variable. It didn't really read this properly, because it doesn't split it into 2 columns. So I think that this is the wrong separator, actually. Because it's not a tab separated file, this. It's not a tab here, it's just a single blank, I think. So let's replace this. The \t is tab, right? But a blank is like this. Let's read it again. This is something you have to, yeah, now it looks like it's 2 columns. Yeah, this is better, right? This is better. So then we have, the next is just to make a figure. And what did should we actually plot? Well, we should of course plot we should use the geom call and display the second column versus the first, okay? So then we just use this jelly table then as input to ggplot, because this is the data we are going to plot. Geom call, and on the x-axis we put, yeah, let's have a look. The first column is called Kamer counts, the second one count counts. Kamer counts. Was this properly typed? And this one was called count counts. Yeah. If you mistype the column names, it will not work, of course, but I think I typed correctly now. And then some xlim here. Yeah, this is something you can skip if you like, but this is just to put some limitations on the x-axis, because I think there are some values in this column here which is super big. Let me see. Kamer counts, the first column. If you scroll down, you can see here is 100, yeah, and there are some values who are super big here. If we scroll all the way down, yeah, 5,000, okay. Yeah, you can experiment by removing this and see what, but then only sort of the plot becomes very difficult. It's almost sort of empty. And of course, in order to display the figure, we have to print this figure object, right? We store the plot in a figure object and then we print it. Like this. Yeah, and this is how it looks like now. Or we can actually zoom it up like this. And this is typical. We have super many Kamers that only occur once. But we can see that out here we have sort of a bulk also of Kamers, and these are the ones who appear the number of times that they should actually, right? Because these are around the camera coverage. We will talk. Let me click this away again. So it says here you could actually, in order to make this figure a little bit prettier, you can scale, or you can put in some mutate the counts like this, so that you say that, okay, values bigger than 5, what's this, 50,000, 500,000 or something like that, should be set to 500,000. Or you can actually put in a limitation on the y-axis as well, I think. Like this. Let's try. Yeah, so then we simply sort of cut this big bar here out, so that we blow up the smaller parts, you could say, so we can actually see the shape of this distribution here. But remember, this the couple of bars here were now removed, right? Because they are too tall. So actually using this y-lim is not as nice. Perhaps we should do as suggested here then, and put in this code here, and then I do it directly after I read the table. Like this, I immediately mutate the counts, and this pmin function, you can look it up. This is very nice. It says that take the values here, and in case some of them are bigger than this value, set them equal to this value. So if I now run the code, read the table again and do this, and then do the printing, we will see that these bigger bars, they should actually go higher, right? But now they stop here at 5 times 10 to the power of 5. And then we can actually see this here. Otherwise, this was almost flat, right? So here we can see the majority, or this is how k-mer counts should look like. But apparently, many k-mers come out with a very low frequency, indicating there's something wrong with these k-mers. There are some sequencing errors here, since they only occur once or twice. So that's the most striking observation here. You have two groups, right? You have the k-mers who appear as often as we should expect them to, and we have the other k-mers who appear very few times. Okay. So the next exercise here is actually repeating what we did now, but for a slightly different data set with error-free reads. So what is this? These are actually simulated reads where we have simulated with no sequencing errors. That's possible when you simulate. So the only reason we will look at this is to see how should this actually look like if reads were without any sequencing errors. So what we do now, we go back to the jellyfish shell script, and we have to change now the input files, right? We no longer use these, so I just copy and I put in, I paste them in again, actually. Then I comment out this, I put a comment, right? So it's no longer used, but I don't delete it because I may go back and use it again later. So what I do now, I just simply edit this for the new file names. And first of all, notice this is in a different folder. It's in the module 3 folder under this courses bin 310. And the files were almost the same name, but they have this underscore Errorfree inside. So if I go into here now and replace module 2 with module 3, that's the first thing I need to change. And then inside the file name, Errorfree, like this. Or was it a capital F? No, only small letters. Errorfree. And underscore. like this. This should be correct, right? Yeah, I think so. Let's try. And then we simply just save the script again, and we go to the terminal and sbatch again, the same script. You don't really need to have separate script for this. You can, of course, put them into two separate, but I keep it in the same now because it's almost identical, right? Almost identical. So now we should, oh, sorry. I've made an error here now because we were also asked to change the name of that output, right? I think I maybe it's already done, I think. Okay, but let me then just comment in again this. It's nice to see that this type of, you will also do this type of errors, I suppose. Let me now run the old code again to reproduce what I had before, right? This is how it looked like before. Let me just save this. And let me just verify that this has actually finished. Yeah, it has finished. So now I sbash it again and reproduce the result I had before. You can actually look at the time of when the result file was created to verify that this is something that has been created now when you are working with this. So let me repeat this here. Yeah, it's still running. It's been running for 22 seconds, but it shouldn't take more than a minute. Now it's done. Like this, yeah, 6.5 kilobytes. Let me delete these old log files now. I don't need them. And now let me go back and do what I should have done in the first place. I comment this out, and then I comment in again here. And what I should have done previously was to change the name of this output file so that we can have both the original count counts and the new error-free count counts together. Otherwise you overwrite, right? So you destroy the previous result. Now, now I save and I sbatch. Sbatch again. Here it is running, and then if I refresh here, hopefully there should now be a new count error-free file here. Yeah, now the counts file, and there it appeared. Take some, and now it should be done. Yes. So now I have these two files here next to each other, and then we can go into the R script, and we already have the code for the old results, and now I simply just copy this and put it under here, and I just edit the file name here so that I read this other file. So now if I run step by step here and print the first, this was the original one that we saw earlier, and now we read the new results and look at the difference. All the ones down here are now gone. If we look at the previous plot, you can see the peak here reaches, yeah, it has its top at a little bit over 50, but there are plenty of k-mers down here, right? But now with the error-free reads, the top is, yeah, above 50. It looks even higher. Yeah, I'm not sure if the coverage is exactly the same in these two files. It appears that this has a slightly higher coverage. But the big point here is to see that when you have reads without errors, you don't see anything down here. All the k-mers from these reads are within this peak here, this group here. that appears around the k-mer coverage expected value. So this is how an error-free dataset looks like, you could say, if you do k-mer counting. Okay,